We are witnessing something that should not be happening. Right now, at this very moment, an object from beyond our solar system is defying every fundamental expectation we have about how comets behave. And the latest images captured just days ago have revealed a phenomenon that no existing model can explain. I'm talking about 3I Atlas, the third confirmed interstellar visitor to pass through our cosmic neighborhood, and what started as scientific excitement has transformed into one of the most bewildering mysteries modern astronomy has ever encountered. This is not hyperbole. This is not sensationalism. This is the assessment of researchers across multiple institutions who are looking at data that contradicts decades of established comet physics. If you want to follow this story as it develops, because trust me, it is developing rapidly with new observations coming in almost weekly, make sure to subscribe and turn on notifications. What we're about to discuss represents a fundamental challenge to our understanding of interstellar objects, and possibly to our assumptions about the nature of matter itself when it spends millions of years traveling through the frozen void between star systems. Let me set the stage properly, because context matters immensely here. When we detect a comet, whether it originates from the Kuiper Belt, the Oort cloud, or interstellar space, we expect certain behaviors based on well-tested physics. As a comet approaches the Sun, solar radiation heats its icy surface. Frozen volatiles, primarily water ice mixed with carbon dioxide, methane, and ammonia, begin to sublimate, transitioning directly from solid to gas. This outgassing creates a diffuse cloud called the coma, which surrounds the nucleus and can stretch thousands of kilometers in diameter. The solar wind, that relentless stream of charged particles flowing outward from the Sun at speeds exceeding 1 million kilometers per hour, pushes ionized molecules in the coma away from the Sun, forming a blue plasma tail composed primarily of ionized carbon monoxide and other molecular ions glowing from fluorescence. Simultaneously, solar radiation pressure acts on dust particles ejected from the nucleus, creating a separate yellowish-white dust tail that curves gently along the comet's orbital path. Both tails point generally away from the Sun. This is Comets 101. This is what we see with Halley's Comet, with Neowise, with every periodic comet that swings through the inner solar system. The model works. It has worked for generations of observations. Until now, until 3I Atlas decided to rewrite the script entirely. This object was identified as the third confirmed interstellar visitor after 1I Oumuamua in 2017 and 2I Borisov in 2019, and initially, despite its exotic origin, astronomers expected it to behave like Borisov, a relatively conventional comet that happened to come from another star system. Borisov displayed typical cometary characteristics: a clear coma, standard outgassing patterns, a composition rich in carbon monoxide and water ice. Basically, everything you would predict from a comet that formed around a different star but follows the same physical laws. 3I Atlas should have been similar. It was not. From the earliest observations in autumn of 2025, something felt wrong. Observers documented periods where the object brightened significantly without producing a visible tail. Think about that for a moment. A comet near the Sun, actively releasing material evidenced by its increased brightness, but not forming the tail structure that should inevitably result from solar wind and radiation pressure acting on that material. Then, there were sudden brightness spikes, sharp increases in luminosity that occurred without corresponding increases in detected outgassing signatures. The object appeared to have a rotating core, unusual in itself for a comet nucleus, which are typically irregular rubble piles, and spectroscopic analysis revealed emission lines in the coma that did not match the standard profiles of water, carbon monoxide, or carbon dioxide dominated outgassing. Let's look closer at the data because the timeline of observations tells a story of escalating strangeness. In October 2025, Mars orbiters trained their instruments on 3I Atlas as it approached perihelion, the point in its orbit closest to the Sun. Even from that distance, anomalies were apparent. Then came early November. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, currently on its complex journey toward the Jovian system, executed a targeting maneuver to observe 3I Atlas during its closest approach to the Sun. Now, JUICE was 66 million kilometers away from the comet, farther than the Mars orbiters had been during their October observations, but the timing was critical. JUICE caught 3I Atlas just after perihelion, when solar heating should have driven cometary activity to its absolute peak. Mission controllers commanded 5 of the spacecraft's science instruments to lock onto the target. Due to communication time lags and bandwidth constraints, only a preliminary quarter-resolution image from the navigation camera was immediately transmitted to Earth. That single image, even at reduced resolution, was remarkable enough that mission scientists broke protocol to release it publicly. It showed a clearly visible coma and what appeared to be dual tail structures, a plasma tail extending toward the top of the image frame, and a fainter dust tail stretching toward the lower left. Dual tails are not inherently unusual, as I mentioned. Comets routinely develop both plasma and dust tails simultaneously. What made this image noteworthy was the sheer clarity of the separation and the hint that something more complex might be occurring, though at quarter resolution, definitive conclusions were impossible. The full scientific data set from JUICE, high-resolution images from the spacecraft's Janus camera system, spectrometric data from MAGIS covering wavelengths from visible to infrared, composition analysis, particle environment measurements, all of that information is currently stored in the spacecraft's memory banks and will not be transmitted to Earth until February 2026. The data transmission bandwidth from a spacecraft beyond the orbit of Mars is limited, and JUICE's primary mission focuses on Jupiter's icy moons, not interstellar comets. So we wait. But while we wait for that definitive data set, other observations have continued, and they have raised the stakes considerably. Enter Professor Avi Loeb from Harvard University, a figure who needs little introduction to anyone following astronomical controversies over the past decade. Loeb analyzed post-perihelion images of 3I Atlas using photometric techniques to estimate the spatial distribution of reflective material around the nucleus. His conclusion, published through his research channels in late November, was startling. According to Loeb's calculations, 3I Atlas appears to be surrounded by numerous objects, and I'm using the term objects deliberately because the data does not conclusively indicate whether these are fragments, ejected boulders, ice chunks, or something else entirely. His analysis suggests these objects lie approximately 54,000 kilometers closer to the Sun than the comet's nucleus itself. Here is the crucial detail. How did Loeb arrive at this estimate? The evidence comes from 3I Atlas's non-gravitational acceleration, a term that refers to changes in a comet's trajectory that cannot be explained by gravitational forces alone. When a comet outgasses, the jets of sublimating material act like tiny rocket engines, producing thrust that alters the object's path. This is well documented and routinely accounted for in orbital calculations. But 3I Atlas is accelerating away from the Sun faster than expected given its observed outgassing rate, as if it is shedding mass or leaving material behind in a manner not typical of standard cometary jets. Loeb's analysis of the brightness distribution suggests that the cluster of objects surrounding the nucleus has a total surface area far exceeding that of the nucleus itself, and accounts for approximately 99% of the visible brightness we observe when we point our telescopes at 3I Atlas. 99%. Think about the implications of that number. We are not looking at a comet nucleus with a coma. We are looking at something surrounded by a cloud of reflective debris that completely dominates the optical signature. And there's more. Loeb noted that the shape of the coma is unusual, described as teardrop-shaped, but pointing toward the Sun rather than away from it. This contradicts what we previously thought about cometary coma dynamics. Normally, the densest part of the coma surrounds the nucleus, and as material streams away under the influence of solar wind and radiation pressure, the coma elongates in the anti-solar direction, creating the characteristic tail pointing away from the Sun. A coma that points toward the Sun implies that material is either being gravitationally focused in that direction, which makes no physical sense given that the Sun's gravity acts equally in all radial directions, or that some other force or process is organizing the distribution of material in a way we do not currently understand. Loeb himself framed this as a puzzle, not a solution, and the broader astronomical community has responded with a mixture of intense interest and cautious skepticism, as is appropriate when dealing with data interpretations that challenge fundamental models. Simultaneously, a team of Spanish researchers from the Institute of Space Sciences, led by Josep Trigo Rodriguez, reported their own surprising findings. Spectroscopic analysis indicated signs of cryovolcanic eruptions on the surface of 3I Atlas. Cryovolcanism involves the eruption of volatiles like water, ammonia, or methane rather than molten rock, a process observed on moons like Enceladus and Triton, where subsurface oceans or reservoirs of liquid or slushy ices break through to the surface. Detecting cryovolcanic activity on a comet nucleus is unexpected but not impossible if the object has sufficient internal heat, perhaps from radioactive decay of long-lived isotopes or from residual heat trapped during formation. What made the Spanish team's findings particularly perplexing was the compositional similarity they detected between 3I Atlas and trans-Neptunian objects within our own solar system. Trans-Neptunian objects, or TNOs, are icy bodies orbiting beyond Neptune, remnants from the early solar system that never accreted into planets. They are composed of primordial ices and rocky material that has remained largely unaltered for 4.6 billion years. If 3I Atlas, an object that formed around a different star in a potentially very different protoplanetary environment, shows compositional similarities to our TNOs, what does that tell us? Does it suggest that planet formation processes are more universal than we thought? producing similar materials regardless of stellar environment? Or is there something about the interstellar medium, the cold, radiation-bathed void between stars, that homogenizes the surface chemistry of objects traveling through it over millions of years? Both are possibilities. Neither is confirmed. So, what does this actually mean? It means we are gathering pieces of a puzzle without yet seeing how they fit together. Then came early December, and everything escalated. Sebastian Voltmer, a highly skilled astrophotographer known for capturing detailed images of comets and nebulae, turned his equipment toward 3I Atlas and obtained an image that has electrified the global astronomical community. The photograph, which has now been circulated widely among professional and amateur observers, clearly shows two distinct tails pointing in opposite directions. Read that sentence again. Two tails, opposite directions. One tail behaves exactly as standard comet physics predicts. It is blue, indicating ionized molecules, primarily carbon monoxide ions, fluorescing under ultraviolet sunlight, and it streams away from the sun, carried by the solar wind at velocities that can reach 400 kilometers per second during periods of high solar activity. This is textbook. This is exactly what every cometary model predicts. But the second tail defies that textbook entirely. It is green, sharply defined, narrow, dense, and it points directly toward the sun. Not slightly offset, not at some ambiguous angle that could be explained by orbital geometry, directly toward the sun, against the solar wind. Let's look closer at the data, because this is where the mystery deepens into true scientific crisis. Spectral analysis of the green tail indicates that the glow originates from nickel ions. Nickel is not uncommon in comets. It has been detected in trace amounts in the comet of several comets, typically appearing as green emission lines around 5,000 angstroms when nickel atoms are ionized by solar ultraviolet radiation and then fluoresce. But never before has nickel been observed forming a dense, organized, directed tail structure. The presence of nickel ions itself is not the anomaly. The organization and directionality are. Under normal circumstances, nickel atoms released from a comet nucleus would be ionized and swept away by the solar wind along with all the other ions, contributing to the blue plasma tail. They would not form a separate green tail, and they absolutely would not stream toward the sun. Solar radiation pressure and the solar wind both act outward. There is no known natural mechanism that would organize metallic ions into a narrow beam and accelerate them sunward against the relentless outward flow of the solar wind, which exerts a pressure of several nanopascals at Earth's distance from the sun, weak by terrestrial standards, but more than sufficient to push ionized gas away from the sun over time. Now, antitails are a known phenomenon in cometary astronomy, so we need to address that immediately. Antitails are diffuse structures that appear to point toward the sun, but they are optical illusions created by viewing geometry. When Earth passes through or near the plane of a comet's orbit, dust particles that have been left behind along the orbital path can appear to form a tail-like structure pointing sunward, simply because we are looking edge-on at the dust trail. Antitails are typically faint, broad, and composed of dust particles, not ionized gas. They fade quickly as viewing geometry changes. The green structure in Voltmer's image does not match this description. It is not diffuse, it is sharply defined, narrow, and bright. Spectroscopy indicates ionized nickel, not dust, and it appears simultaneously with the blue plasma tail, both structures clearly separated and behaving independently. Standard models predict that materials ejected from a single nucleus should mix in the coma, disperse under solar wind pressure, and stretch along similar trajectories dictated by the combined influences of the comet's velocity, solar gravity, radiation pressure, and the solar wind. The fact that we are observing two completely independent tail structures, one behaving normally and one behaving impossibly, contradicts the foundational assumption that a comet nucleus ejects material into a single shared environment where physical forces act uniformly on all particles according to their mass and charge. This is not the first anomaly 3I Atlas has presented, and that is what makes this so profoundly unsettling. Voltmer's image is not an isolated oddity. It is the latest in a cascade of unexplained observations stretching back months. Independent observers equipped with telescopes ranging from backyard instruments to university observatories have documented all of the following: periods where 3I Atlas exhibited high brightness with absolutely no visible tail structure, a configuration that violates the basic principle that if solar heating is causing sublimation, there must be outgassing, and if there is outgassing in the presence of solar wind, there must be a tail. Sudden brightness spikes occurring over intervals of hours without corresponding increases in coma size or spectroscopic signatures of increased volatile release, suggesting that the brightness changes may not be driven by outgassing at all, but by some other mechanism, such as rotation bringing more reflective surface into view, or even active emission from the surface itself. A clearly defined rotating core, visible in high-cadence photometry, implying a level of structural coherence unusual for a typical cometary nucleus, which are often loosely bound aggregates of ice and rock. Emission lines in the coma that do not match the standard water-carbon, monoxide-carbon dioxide profiles, hinting at unusual volatile composition or unexpected chemical processes occurring in the coma environment, and multiple independent detections of anti-tail structures by observers using different instruments and different observing sites, ruling out the possibility of a single instrumental artifact or processing error. Each observation, taken individually, could potentially be explained by some combination of unusual but not impossible factors. Taken together, they paint a picture of an object that is fundamentally not behaving like any comet we have studied in detail. And this raises a question that has been circulating in observatory backchannels and online forums, frequented by serious amateur and professional astronomers. Are we actually observing a comet, or are we observing something else masquerading as one? I want to be extraordinarily careful here because this is where speculation can run wild and undermine the credibility of legitimate scientific inquiry. The data do not support jumping to exotic conclusions. The data support saying clearly and firmly that we do not understand what is happening. Could 3I Atlas be a fragmented object, a comet nucleus that broke apart either recently or in the distant past, with multiple components of different compositions responding differently to solar radiation? Possibly. Fragmentation events are well documented in cometary science. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before impacting Jupiter in 1994. Comet 73P Schwarzmann-Wachmann 3 has fragmented multiple times, producing dozens of observable fragments. Fragmentation typically produces observable changes in brightness and coma morphology as newly exposed volatile-rich surfaces begin outgassing. But if the fragmentation occurred long ago and the fragments have since developed insulating dust mantles, the brightness and morphology changes might be subtle or delayed. However, and this is critical, we have not observed the kinds of brightness fluctuations and fragment trails that typically accompany active fragmentation, which leaves the fragmentation hypothesis intriguing but not fully satisfying. Could 3I Atlas contain a complex internal structure composed of distinct layers or pockets of material with wildly different compositions, perhaps ices rich in different volatiles, or even metallic inclusions? And could differential sublimation of these materials produce the unusual tail structures? Again, possibly. Comets are known to be heterogeneous. Sample return missions like Stardust, which collected particles from Comet Wild 2, revealed a mixture of materials including high-temperature minerals that likely formed near the Sun and were later transported to the cold outer solar system during the early chaotic phase of planetary migration. If 3I Atlas formed in a protoplanetary disk with unusual chemical gradients or underwent collisional processing that mixed diverse materials, it might contain pockets of metal-rich material that sublimate or are ejected differently than water ice. But this still does not explain the sunward directionality of the green tail. Differential sublimation can create asymmetric outgassing, producing jets that can alter a comet's rotation and trajectory, but it cannot reverse the direction of the solar wind or radiation pressure. The force vectors still point outward from the Sun. There is another layer to this story that cannot be ignored, though it exists in a more ambiguous and contentious space. Within the community of amateur astrophotographers and independent observers, there have been persistent discussions about discrepancies between images released by official space agencies and those captured by independent observers. Some have pointed to instances where NASA or ESA images of 3I Atlas appeared blurry or lacked detail in regions where independent ground-based observers using sophisticated equipment recorded dense, well-defined structures. I need to be clear about what this does and does not imply. Image quality depends on countless factors: the resolution and sensitivity of the instrument, atmospheric seeing conditions for ground-based observations, the signal processing and compression applied to images before public release, the specific wavelength filters used, and the exposure time. Space-based instruments observe from above the atmosphere and avoid seeing distortion, but they are often located at great distances from the target and may have different resolution capabilities than large ground-based telescopes equipped with adaptive optics. There are entirely mundane explanations for why different instruments produce different-looking images of the same object. However, the perception of discrepancy, whether ultimately justified or not, has fueled speculation and distrust, and it contributes to the broader sense that something about 3I Atlas is not being fully communicated or understood. I include this not to endorse conspiracy thinking, which I emphatically do not, but because part of the story of 3I Atlas is the way it has challenged not just scientific models, but also the social dynamics of astronomical observation in an era where amateur astronomers equipped with CCD cameras and spectroscopes can produce data rivaling that of professional facilities. What do you think is actually happening here? Are we looking at a comet with an unusually complex composition and structure that happens to produce these bizarre behaviors under specific solar conditions? Or is there something more fundamentally strange about this object that we have not yet conceptualized? Drop your thoughts in the comments, because this is the kind of question where the collective insight of an engaged and informed audience can sometimes identify angles that individual researchers might miss. And I genuinely want to know what you think the February 2026 data release from JUICE will reveal. As 3I Atlas continues its journey deeper into the inner solar system, moving along a trajectory that will eventually bring it relatively close to Earth, its behavior is not stabilizing. If anything, the object is becoming more erratic. Brightness continues to fluctuate unpredictably. Tails appear and disappear. The green sunward-pointing stream of metallic ions persists in images captured by multiple independent observers, defying every attempt to reconcile it with standard physics. Researchers are preparing observation campaigns using every available telescope, from ground-based arrays to space telescopes not primarily designed for solar system observations, but capable of being retargeted. Spectroscopy will be critical. If we can obtain high-resolution spectra of both the blue and green tails simultaneously, we can identify the exact ionization states and velocities of the particles in each tail, which will provide constraints on the energies and forces acting on them. Photometry across multiple wavelengths will help determine whether brightness variations correlate with rotation, outgassing events, or something else. Radar observations, if 3I Atlas comes close enough, could potentially reveal the size, shape, and surface properties of the nucleus directly. But the real hope, the data set that might actually crack this mystery open, remains locked in the memory banks of the JUICE spacecraft. In February 2026, those high-resolution images and spectra will begin their transmission to Earth. We will see the nucleus, assuming the images resolved it, at a level of detail no ground-based telescope can achieve. We will have spectroscopic data covering a broad wavelength range, from ultraviolet through visible to near-infrared, revealing the composition of the coma and potentially the nucleus surface. We will have particle environment data, measurements of the charged particle flux and magnetic field in the vicinity of the comet, which could reveal whether there are unexpected electromagnetic interactions occurring. That data could provide answers. It could confirm that 3I Atlas is a comet with a highly unusual but ultimately explainable composition and structure. Or it could deepen the mystery further by revealing details that fit no existing model. We do not know, and that uncertainty is both the frustration and the thrill of this moment in observational astronomy. So, what does this actually mean for the broader picture of our understanding of comets and interstellar objects? It means we may need to reconsider assumptions we have held with confidence for decades. The standard comet model is based on observations of hundreds of comets, but the vast majority of those comets originated in our own solar system, formed 4.6 billion years ago from the specific mixture of materials present in our protoplanetary disk and processed by the specific radiation and dynamical environment of our Sun and planets. Interstellar objects like 3I Atlas formed elsewhere around stars that may have been more massive or less massive than our Sun, in protoplanetary disks with different chemical compositions, and then spent millions or even billions of years traveling through the interstellar medium, exposed to cosmic rays and the faint background radiation of the galaxy. Is it possible that this history produces objects with material properties or internal structures so different from solar system comets that our models simply do not apply? Absolutely, that is possible. Is it possible that we are missing some fundamental physical process, some interaction between solar radiation or the solar wind and certain types of material that we have never encountered before, because solar system comets do not contain that material in sufficient quantities? Again, possible. Or, and this is the question that hangs unspoken in every conversation about 3I Atlas among researchers, is it possible that what we are observing is not a natural object in the sense we usually mean, but something else entirely, something that formed or was modified by processes we do not yet have a framework to understand? I am not endorsing that interpretation. I am simply acknowledging that when you exhaust conventional explanations and the data continue to defy those explanations, you must at least entertain the possibility that your framework is incomplete. The fundamental challenge of 3I Atlas is that it sits at the intersection of multiple unknowns. We have limited data on interstellar objects because they are rare and difficult to observe. We have limited understanding of the material properties of objects that have spent eons in interstellar space. We have limited models for the behavior of comets with complex or heterogeneous internal structures, because most of the comets we study in detail are relatively simple icy bodies. And we are observing 3I Atlas at a unique moment in its trajectory, during perihelion passage when solar heating is at maximum and activity is most intense, but also most chaotic. All of these factors combine to create a situation where the data are rich, but interpretation is maddeningly difficult. Here is what we know with high confidence. 3I Atlas is an object, approximately a few kilometers in diameter, based on brightness and assumptions about surface reflectivity, that entered our solar system from interstellar space on a hyperbolic trajectory, indicating it is not gravitationally bound to the Sun. It has passed perihelion and is now heading outward, though still within the inner solar system and on an approach trajectory that will bring it relatively near Earth in the coming months. It exhibits cometary activity, outgassing, and coma formation, confirming that it contains volatile materials that sublimate when heated by the Sun. It has displayed a blue plasma tail consistent with ionized gas being carried away by the solar wind. And it has displayed a green tail, apparently composed of ionized nickel, that points toward the Sun in direct contradiction to the expected direction of solar wind and radiation pressure forces. All of these facts are supported by multiple independent observations. The challenge is constructing a coherent physical model that accommodates all of them simultaneously. If this video has given you a deeper appreciation for just how strange this situation is and how significant the implications could be for our understanding of the universe, hit that like button, because it genuinely helps push science content like this to a wider audience on YouTube. And right now, we need more people paying attention to what is happening in our own cosmic backyard. The algorithm rewards engagement, and the more people engage with deep analytical science content, the more the platform will prioritize it, which means more resources and attention for the researchers doing this work, and more public awareness of discoveries that might reshape our understanding of reality. The question that crystallizes the entire mystery, the question posed by one observer recently and now repeated in observatories and online forums around the world, is this: if 3I Atlas is not a comet, then what exactly is it? And perhaps more unsettling, if it is a comet, but one so different from every other comet we have studied that none of our models apply, what does that tell us about the diversity of objects in the galaxy and the limits of our current understanding? We build models based on available data. For centuries, all available comets were solar system objects. 3I Atlas is forcing us to confront the possibility that solar system comets are a small and perhaps not representative sample of the comets that exist in the galaxy. If comets from different star systems, formed under different conditions and processed by different environments, behave in fundamentally different ways, then every assumption we make about comet populations in exoplanetary systems, about the delivery of water and organics to planets, about the role of comets in the chemical evolution of planetary systems, all of that may need to be revisited. And there is a deeper, more philosophical implication. 3I Atlas is a messenger from another star system, carrying information about conditions and processes in a place we can never visit. Every measurement we make, every spectrum we record, every image we capture is a piece of a message written in the physics and chemistry of an alien environment. Decoding that message requires not just sophisticated instruments, but also the intellectual humility to recognize when our existing frameworks are insufficient and the creativity to imagine new ones. Science advances not just when we confirm what we expect, but when we encounter phenomena that shatter our expectations and force us to think differently. 3I Atlas is that phenomenon. It is the anomaly that does not fit. And history tells us that anomalies like this, when investigated rigorously and honestly, often lead to breakthroughs that redefine entire fields. The coming months will be critical. As 3I Atlas moves through the inner solar system, observation campaigns will intensify. More telescopes will be trained on it. More spectra will be taken. More images will be captured. The object will eventually pass closest to Earth, offering the best possible viewing geometry and the highest resolution observations ground-based instruments can achieve. And then, in February 2026, the JUICE data will arrive, potentially bringing the resolution, literally and figuratively, that everyone is waiting for. Until then, we watch, we measure, we hypothesize cautiously, and we acknowledge the profound uncertainty at the heart of this mystery. 3I Atlas has already secured its place in the history of astronomy as one of the most perplexing objects ever observed. Whether it will also become the object that forced us to fundamentally rethink our understanding of comets, interstellar matter, or something even stranger, remains to be seen. But one thing is certain: the universe has sent us something we were not prepared for. And how we respond to that challenge will define the next chapter of our exploration of the cosmos. The mystery of 3I Atlas is not just a puzzle to solve. It is a reminder that no matter how much we learn, the universe will always have the capacity to surprise us, to humble us, and to invite us to look deeper.